everyone. Good afternoon and good morning. We've taken a break in our webinar schedule through the summer and busy season, so welcome back and welcome to today's webinar, Soil, Steel Structures, and End Treatments, Design Basics. Presenting today are Heba Ahmed and Drew Wilms from Armtec-Drainage Solutions Business Unit, both of whom I'll introduce more shortly. My name is Janine Yetke, Director of Marketing, and my group runs Armtec-Drainage Solutions webinar program. I'll be your host for today's event. We also have James Carter on the line, who is our technical moderator and who will be running questions and answers at the end of the session. I'll quickly go over some housekeeping items. At any time during the presentation, if you have questions, please enter your questions into the question log. We will get to the questions at the end of the session. As a reminder, attending this session will qualify you for a 1-hour technical informal CPD credit. For those who have registered directly, we will send out the certificate to the email provided upon login. For those who are attending as a group, please compile your list of attendees and send the attendance list with the required details to webinars@armtec.com. I'd like to start off with a brief introduction to Armtec. We are one of Canada's oldest and largest infrastructure companies, supplying a full range of steel and HDPE-based bridge and culvert materials, as well as soil retention, stormwater management, and precast building systems. Because of our convenient locations across the country, we are well positioned to serve your needs wherever you are. We serve numerous sectors from municipal to forestry and transportation to commercial, retail, and residential construction. More about how we service these sectors can be viewed on our website or through discussion with one of our experienced sales representatives. With our centralized engineering department and regional engineers, Armtec has the exceptional capability to fully support design and challenging engineered project requirements. Please call on us. Presenting today are Heba Ahmed and Drew Wilms. Heba is a National Product Manager and Regional Engineer for Ontario with Armtec and has expertise with the design of various Armtec Drainage Solutions products, including buried steel structures such as multiplate and bridge plate structures. Drew Wilms is the Regional Engineer for British Columbia and supports Armtec's full portfolio of stormwater management and engineered solutions, including bridge plate, multiplate, and retaining wall products. Both of them look forward to plenty of questions today, so please feel free to ask questions at any time through the interface. And now I will pass the presentation off to Heba. Welcome, Heba.
Okay, hello everyone. Thanks for joining us today. Here's a look at today's agenda. We'll begin with a general overview of different bridging solutions, but we'll really zero in on soil steel structures just to highlight some of the benefits and applications for these solutions. We're going to go over some structural and durability design basics, as well as the process of selecting the appropriate end treatment. We're going to finish off with some case studies, and we're hoping that by the end that you're getting more comfortable with the concepts of buried bridge and soil steel design. So as mentioned earlier, Armtec manufactures different materials for the bridge solutions. So here's what we can offer in terms of options for these bridging solutions. The materials can be either precast concrete or corrugated steel options for the portfolio we're going to be discussing today. And selection of material really depends on a number of factors, including the project application, any loading conditions, also a consideration to internal or external clearance boxes requirements, which will basically dictate the geometry of your structure. Hydraulic conditions and considerations are also very important in water crossing applications, as well as the location and installation methods for these projects. For instance, if the project is located in a remote location where mobilization of heavy equipment is a challenge, this may warrant the use of lighter material that can be installed with lighter equipment. A major factor in many cases, as everyone knows, is cost. So contractors as well as owners must be consider the total installed cost when assessing the different options. This obviously extends beyond the cost of the material itself to also include the cost of backfill material, lifting equipment, and shipping or freight. So keeping all these factors in mind, here are some of the options available for the buried bridge profile we're going to be discussing today. Starting at the top, you can see a picture of it on the left-hand side here, is a structural steel box culvert. It's well suited for low headroom applications and is offered in sizes ranging from 4 meters to about 15 meters in clear span. The next one showing here is the multi-plate and tunnel liner profiles, which are both shallower corrugations and are typically designed economically for spans between 3 and 7 meters. Beyond that, however, they can be used to construct larger spans. However, they will require special features to be able to do that. To get away from that, our deep corrugated profile bridge plate is utilized to construct larger spans and can be supplied anywhere between 6 meters to about 21 or 22 meters in span, without the need for any bracing or special features. Beyond these span ranges, you can also design buried bridges using precast solutions to accommodate up to 32 or 33 meters in clear span. That can be achieved with our segmental precast arch units. The one that Armtec carries is the BEVEL arch segments. But today, as I mentioned, we're going to be focusing on the steel options to highlight some of the relatively recent developments in that product group and showcase some of the efficient and cost-effective aspects of buried steel bridges. So segmental structural steel products are not new to the marketplace. They've been around for over 85 years, and throughout the years have undergone different advancements since their introduction to the marketplace in the 1930s. These products have developed further to enhance profiles, extend the span ranges offerings, as well as introduce new coating options to tackle durability. As everyone knows, that's a big item. As you can see from the representative list of projects here, these products are backed up with a solid history of successful bridge installations, dating back as early as the 1960s on larger spans. These structures are still meeting their service life to date, and in some cases are exceeding the service life requirements. One of the main benefits of structural plate products is the fact that they are segmental. So they can be easily and economically stacked and shipped on a single truck bed or loaded up in containers to be shipped internationally. They're very easy to install without the need for any large cranes or special equipment. And while there are standard sizes and shapes available, these products are very customizable and can be manufactured to fit different project requirements. Also, since these are bolted plates, it's quite easy to extend an existing structure for future road widening. This is done by just exposing the ends of the existing structure and bolting on new plates to extend its length, obviously after conducting a survey of the structure to ensure a proper fit. With some of the recent developments in coating options and design for durability, these structures can easily provide a design service life of 75 and in some cases 100 years. Material options within a certain span range. So as such, they can provide the lowest life cycle cost in that span range. And because of their flexible nature, they're well suited for a wide range of loading conditions. This relies on the fact that these structures can flex to shed loading on the surrounding backfill envelope. So from deep, bury, or high fill situations to heavy haul truck loading in mining applications, these structures can accommodate significant dead and live loads. They're also often designed for railway vehicles. So typically each structure has significant reserve capacity as well for overload conditions due to its flexible nature, and can be designed for seismic forces as well. Other benefits include the fact that you can eliminate bridge deck and the icy deck deterioration problems that are normally associated with that. Eliminating the cost of bridge maintenance adds to the overall cost savings of the structures as well. And due to their natural appearance, these structures are environmentally preferred with their natural earth slope and vegetation appearance. So a bit more detail on the multi-plate profile. Multi-plate has a 6 by 2 inch corrugation, or if you're metric, the translation is 152 measuring from crest to crest, and the depth of each corrugation is 51 millimeters. The product is available in 5 different thicknesses, from 3 millimeters up to 7 millimeters. And there are different shapes available and can be manufactured in different configurations. As you can see, there are full periphery structures. Some of the common ones are pipe arch shapes for low headroom applications, and there are also open bottom structures available. There are also different coating options, and we're going to be talking a little bit in more detail about that. But basically, the structures can be either galvanized or polymer coated, or in some cases, both, as you can see in the picture on the slide here. For this structure, it's a full periphery structure where the invert plates were polymer coated, and the balance of the structure was left galvanized. Some of the most common applications for this product group is in drainage culverts and underpass structures. However, this product has been utilized quite extensively in other types of applications due to its flexible nature again, such as conveyor tunnels and mine portals. Municipalities often have short to medium span bridges needing replacement or rehabilitation, and multiplate is a very economical option for that. For rehab applications, multiplate is often installed using a slip line method to reline an existing deteriorating structure without the need to dig out the road. So this technique can be used by municipalities to stretch out their budget dollars. The bridge plate product was developed in the late 90s, and it's a true metric corrugation. The profile here measures 400 millimeters crest to crest, and the depth of the corrugation is 150 millimeters deep. This, as you can imagine, is a much stiffer section, and as such can be used to construct much larger spans without the need for any special features, which would otherwise be required in the multiplate corrugation. And similar to multiplate, bridge plate is also available in 5 different thicknesses, ranging from 4 mil all the way up to 8 millimeters. Each plate is 3 corrugations wide and measures 1,200 millimeters. These wider plates allow for faster assembly times in the field. Obviously, time is money, so that also allows for further economies. The same coating options that are available for multiplate are also available for bridge plate. And the bridge plate applications, while similar to those identified for multiplate, are possible in much larger clear spans and a wider range of magnitude of loads. Here are some of the most common shapes encountered in bridge plate applications. Arches are available in 3 shapes: single radius, low profile, and high profile arches. There's also a wide range of box culvert shapes available, and with its low rise to span ratio, these are ideal for low profile and low cover applications. Where foundation bearing capacities are an issue, round structures work well and can be manufactured up to 15 meters in diameter for the bridge plate profile. Just a quick comparison on the 2 profiles side by side. You can see on the bottom left-hand picture here, the top plate is that of a multi-plate corrugation, and the bottom is a bridge plate section. The generic term for the shallower plate shown on top is SPCSP, or structural plate corrugated steel pipe. And for the deep corrugation located on the bottom here, the term is DCSP, or deep corrugated structural plate. Both products involve segmental plate construction, whereby individual plates are corrugated, punched, and curved. Then a complete ring is assembled of 2 or more plates of sufficient length to match the required total circumference of the defined structure. All Armtec segmental plate products can be customized to accommodate different configurations, fittings, and alignments. As you can see here, different configurations are made possible: T's, Y's, elbows, and bulkheads. And all these sections are completely designed in-house by our engineering team. You can see it's a very versatile product to work with. Okay, so now we're going to dive into some design basics. When looking at a bridge design, it is important to consider a number of factors in order to properly address the needs of the project. I'll cover the structural design element in a bit more detail over the next few slides, but before I do that, here are some other considerations you might want to take into consideration. You'll need to properly size the structure to basically address any roadway clearance requirements in an underpass or grade separation. And in water crossings, you need to address any hydraulic conveyance requirements or end area. Durability, as everyone knows, is a big one, and as these structures need to last for the intended service life, they do need to be designed appropriately with a consideration to the specific environmental parameters of the site you're looking at. So we'll be covering how to do that today. An equally important consideration is the alignment and location of the structure to ensure that the natural stream slopes are accommodated and not disturbed, and also that the structural backfill is applied in a balanced manner to prevent an unbalanced loading condition. Selecting the appropriate end treatment for the application is another piece of the puzzle, and we'll be going over that criteria today as well. And finally, having an environmental impact mitigation plan for the project. So I wanted to mention that the CSA standard G40114 governs all the material fabrication and inspection criteria for corrugated products. This also includes the coating, as well as the galvanized, as well as the STRATA-CAT or polymer coating presented here. You can download the CSA publication on the website. As far as design codes, as the physical size of the culverts increase, the structural design is required to be in accordance with bridge codes. So in Canada here, the Canadian Highway Bridge Design Code, or CSA S614, is accepted across the country. This bridge code demands structures greater than 3 meters in span to be designed in accordance with Section 7, which is titled Buried Structures. So basically treating every structure over 3 meters as a buried bridge. If, however, you're considering a structure under 3 meters, these can be designed using AASHTO or ASTM codes, which follow the theory of rim compression. The American Iron and Steel Institute did extensive research in the late 50s and 60s on rim compression design theory, and this method is now detailed in the Handbook of Steel Drainage and Highway Construction, which you see a picture of the cover here on the screen. So speaking of ring compression, we can understand this a little better by looking at the components of a buried structure. A buried soil steel structure consists of a steel shell and a soil backfill envelope with no geotechnical properties. The idea here is that with the radial geometry of the steel shell, the loads are dispersed into the engineered backfill envelope. From there, these loads are transformed into radial loads known as axial compressive thrusts. A corrugated shell is a highly efficient section to support axial compressive loads. So by combining these two components, the end result is an economical buried structure that's usually capable of supporting large loads. As with any composite member, the load resistance of the composite system is influenced by the properties of each member. So here the geotechnical properties of the backfill envelope are crucial to determining the load resistance of that system. Also, the geometry of the buried shell and the stiffness of the plate elements will influence the magnitude of forces drawn to the structure. So the stiffer the member, the more load is attracted to it. Force analysis considers all axial thrusts, bending moments, and deflections taking place during and after construction. The strength analysis then considers the resistance available from plate elements to support the calculated load effects. And obviously, in the end, the resistance of the design section must exceed the load demands on the structure. So the very first step in the design process is basically to determine the minimum cover on the structure. And here the minimum cover is measured to the uppermost corrugation crest of the section, as you can see on the diagram. So whether it's a single corrugated plate that's being designed or a double shell, that's when you're designing with reinforcing ribs, it will still be measured to the uppermost corrugation crest. The calculation depends on a number of equations that are listed here only for reference. I'm not going to go over them. But basically, it is calculated as the larger of these three values, and it's a function of the span and rise of the structure. One thing to note is that for deep corrugations, the code permits lower covers in larger span configurations to account for the increased stiffness of the plate section. Once minimum cover is established, then the unfactored dead load and live load thrust can be calculated. A basic static calculation using the unit weight of the soil and the dimensions of the soil column above the structure determines the dead load thrust. The live load on the structure is determined by distributing the individual wheel loads through the soil and pavement column to the top of the structure. So the more soil overburden on top of the structure, the less the effect of live load is on the crown. Then the total factor thrust requires applying load factors as well. In this case, it's 1.25 for dead load and 1.7 for live load. An impact factor, referred to as DLA or dynamic load allowance, is also applied to the live load component of the equation. The second formula you see here determines the total thrust for the load combination that includes earthquake loads, if and when seismic loading is to be considered. So obviously the larger of the two values governs and will be carried forward to the next calculation. Similar to any axial stress calculation, the compressive stress in the wall of the shell equals the thrust divided by the wall area. And the wall area here is basically the area of the selected plate thickness. Next, the available resistance and compression of the plate wall has to be calculated. This value depends on the neutral axis radius of the plate in relation to the effective radius, which determines which equation here is going to be used. By definition, corrugated metal structures are flexible. Therefore, design checks need to be made to ensure construction forces do not exceed the design forces experienced in the complete structure. This interaction equation here ensures that all moments and thrust forces experienced during constructions do not cause a plastic hinge that would fail the structure before it's fully backfilled. And similar to the previous step, this interaction equation also considers bending moments and thrust, except this time it's only applicable to deep corrugated structures, and it is for the completed structure, so after all the backfill is in place. And this step recognizes basically that the stiffer buried shells attract load or may be subject to loading conditions whereby significant bending moments can develop. An example of that would be if a structure needs to support heavier than usual axle loading under a modified cover. And last but not least, all bolted structures require a seam strength check to ensure that the factored thrusts do not exceed the factored resistance of the longitudinal bolted seam. It is important to note that all the equations in the CHBDC were developed through finite element analyses for a limited range of sizes and loading conditions. So beyond these limitations, the code will permit the use of rigorous methods of analysis such as finite element modeling in order to capture what the code equations does not capture. So there are a number of different tools available to perform these types of analysis, such as Plaxis and Candy. And modeling of the structure allows each lift or stage of construction to be captured. And in turn, outputs on bending moments and thrusts, as well as deflections against the load resistance of the system, will be available. The next few slides will show a sample of typical reports generated by these modeling tools. So the first one I'm showing here is an example of an axial force diagram for a modeled deep corrugated structural steel box, which clearly shows the effects of axial loads generated by the applied loads. A bending moment diagram of the same structure shows the positive and negative moments at the crown and haunch, which is what you would expect of a frame-like structure. As each step of the model converges, the deflection can be monitored for a certain point on the structure. And here we can see that the maximum deflection of the crown of the completed structure is negligible and well within the allowable tolerance. The model will also provide a stress diagram to show what is happening in the soil. Here you can see the vertical stresses in the backfill envelope, and note that as you go up in elevation, you can see the reduction in vertical stresses as you would expect. Similarly, a horizontal stress diagram will show contours representing the horizontal stresses in the soil envelope at each elevation throughout the model. I will now hand it over to Drew, who will begin by explaining how to design for durability.
Great, well thanks Heba, and yeah, thank you again to everyone for joining us today. So for the last half of the presentation, we'll really be focusing on two key considerations in structural plate design, as Heba mentioned. So firstly, we'll talk about durability and service life considerations. Really here what we want to address is how we can extend the service life of structural plate products, and also talk about how we can design to achieve a particular lifespan based on the project or site-specific conditions. Following that, I'll talk about end treatment selection. So basically, how do we protect these structures to ensure they're not washed away in large storm events, and also we'll discuss basically best management practices to protect them from abrasive flows, things like piping, scour, debris flows, and whatever other conditions might threaten their long-term performance. So those are really the two big design considerations I want to focus on. Following that, we'll go through some high-level applications for primarily deep corrugated structural plate products, as well as a few case studies that I hope are interesting to you, and that also highlight the product capabilities. All right, so firstly, designing for durability. It's certainly an important design consideration for really any corrugated steel product. In order to really get the most value from these structures, it's important that we know and identify the site conditions that will affect the service life of the structure, and also that we specify the correct coating or material to handle those conditions. So essentially there are two ways that we can influence the durability and service life of structural plate. Firstly, we can vary the plate thickness, so we can increase the thickness of the structural plate to add additional service life. And then secondly, we can vary the coating system or material of the plate. So here you can see the variable coating options that are available. The technology has certainly improved over the past few decades. When multi-plate was first developed back in the early 1930s, there were only a few options available. We had basically black steel and galvanizing. So we have a lot more options available to us now. We have a much better understanding of how these coatings interact with the soil and based on the water chemistry. So in terms of galvanizing, we have two different options that are available: 915 grams per meter squared and 1220 as the heavy galvanizing. So the standard in the CHPDC is the 915 grams per meter squared. We do also have aluminum structural plate, primarily just available for our tunnel liner product, so a bit of a specialty application there. And then we also have our STRATA-CAT polymer coating, which Heba introduced as well. The CAT refers to corrosion arresting technology. So really this polymer coating is available for, to address the harshest site conditions, really provide superior resistance to corrosion, abrasion. If we have acidic environments or fairly alkaline environments as well, that's how we address those conditions. So just a bit of an introduction to the product there. The way in which the product or the coating is applied, we take our black steel plate, we sandblast it to clean it, to make sure there's no residue or debris on the plate, and we apply a zinc-rich primer coat, which provides a bit of additional barrier protection, and then also helps the baked-on powder coat adhere properly to the plate. So the powder coat has an ethylene acrylic acid base, and it provides a nice polymer finish layer that's hard, abrasion resistant, and chemically inert. So in terms of the actual STRATA-CAT, the coating process, it's done in a factory environment, very stringently controlled. Make sure we have high quality control and consistent adherence to the plate itself. The process, as I mentioned, includes the sandblasting, so we thoroughly clean the plate, and then we have separate application processes for both the zinc primer layer and then the polymer layer. So in the photo on the left there, you can see the plates have received both the primer coat and then the coating electromagnetically, and they're about to enter the high temperature baking oven, which you can see on the far side here. And then the plates on the right are emerging from the coating process. They're pretty much completed and ready to go. They'll be made ready for shipment, nested, palletized, and then sent off to site. So in terms of actually designing for durability, we have a number of different coating selection criteria. So a few considerations to keep in mind when actually determining which coating or which material is most appropriate. So these charts were actually developed for just corrugated steel pipe, but are still applicable for structural plate products as well. So the main criteria, we have abrasion, pH, resistivity, hardness, and chlorides. So really, how much debris is going to be in the water course if this is a culvert application, and what's the chemistry of the water as well that the plate will be subjected to. So in each of these charts, you can see that the polymer coating really provides the best option in terms of addressing difficult chemistry considerations as well as high abrasion within the water course. And then we have aluminum or aluminized steel as well, addresses those fairly well, and galvanized steel definitely has far more limited applications. So in terms of actually designing in terms of service life, this diagram outlines really the typical approach that we take for estimating the material service life of any structural plate product. So this one is specific to galvanized steel. The CHBDC doesn't actually dictate a specific durability estimation procedure. So typically we revert to loss models that are provided by AASHTO and other white paper studies. So this estimated material service life approach, this method really is shown how we determine the service life based on the given site conditions that were mentioned on the last slide there. So the loss model that we assume a uniform rate of corrosion for each layer. So assume a uniform amount of material loss for the galvanized layer and then the steel layer beneath. And this model is typically quite conservative. So the nominal structural steel thickness is actually what we designed to accommodate the loading conditions. So this would be the steel thickness that's selected based on the design criteria that Heba has spoken about. And then we will add a corrosion allowance to that thickness to ensure that, throughout the lifespan of the structure, we're able to handle the dead and live loads that we're needing to design for. So this methodology varies slightly when it comes to polymer coated steel. So with the addition of the polymer coat, we actually assume no material loss for a certain period of time. So essentially we have an add-on service life. And then, once we've reached the end of that add-on service life, again, we revert to the same loss model, assuming a uniform rate of corrosion of the steel. So again, we can add additional steel if we need to increase the service life. So the extent of that add-on life provided by the polymer coating is again a function of those other selection criteria, primarily related to chemistry of the water course. Just a couple of photos of the various options that are available. So aluminum structural plate shown on the top there. The top right is our tunnel liner plate product. So it's a two-flange liner. Again, fairly significant applications in terms of culvert and bridge rehabilitation. And then on the bottom here, we have some photos of STRATA-CAT, the polymer-coated plate. As Heba mentioned on the bottom left there, we're really just highlighting that it's rarely actually necessary to coat the entire structure. Usually it's just the side plates or the invert plates if it has a full periphery that really, those are the parts that are subjected to the water. So those are really all we need to polymer coat. We can typically get away with a galvanized crown for the structure. Definitely helps save a little bit in terms of cost. So on the bottom right there was a bit of a unique application where we did coat the entire structure. This was a reline application actually, so we had a structure that was under about 20 meters of fill, so very high height of cover. So really relining was the only option instead of excavating and replacement. But the original galvanized structure was actually buried with acidic drain rock. So we had very acidic leachate on the outside of the structure as well as an acidic water course going through the culvert. pH ranged as low as 3. So a galvanized system definitely wasn't appropriate in this case. We went with a full polymer coating to address those corrosive conditions. All right, so we'll move on to the last portion of the presentation then, certainly not the least by any means, and that is end treatments. So this is a very important consideration. I can't really stress that enough in terms of protecting the structure. We can go through all these design iterations, we can polymer coat the structure, add additional steel thickness, etc. But if it washes out at the end of the day or maybe 5 years after installation, simply because we didn't protect the ends properly, that's definitely a relatively poor return on investment. So the big question is, how do we protect these structures? And so we'll go through a few of the different options in the next few slides. All right, so the first option I'll discuss are steel head walls. So these are fairly common, simple, cost-effective options for soil retention, particularly for low-profile and box culvert bridge plate structures. So essentially what we do, we use corrugated steel walls in either cantilevered or anchored configuration. The corrugated steel can either be our bridge plate corrugation, multi-plate, or sheet piling. Again, the corrugation will depend on the height, the lateral, and moment resistance that are required based on the loading conditions. So essentially we simply connect these corrugated sheets to the structure using rolled angle irons. We would supply these to match the profile of the arch, as you can see in the photos here. The sheets are then fastened to the angle with bolts to provide a tight mechanical connection. So oftentimes you'll see these used in conjunction with bin wall wing walls, as you can see in the photo on the bottom right there. So anchoring is typically required if we have a relatively high wall, high lateral loads. So particularly in cases where we have a high or steep backslope, as shown in the photo here. In those cases, we'll typically fasten angle irons to the front face of the head wall, and then we'll use tiebacks to either the structural plate or a dead men buried in the embankment. So that's what is shown here. So we have the head walls, as you can see, tied back and anchored to the structure itself opposite the head wall. And then the wing walls are actually anchored back via tiebacks and dead men buried in the embankment. So the dead men is essentially just a corrugated steel sheet. So this full system can be designed in-house by Armtec. So bin wall is another steel solution often used in terms of entry for wing wall applications with our structural plate products. Like the rest of the products we presented on today, bin wall is a system made up of corrugated steel components. The components are bolted together essentially to create steel bins, which are then backfilled, typically with a well-graded granular backfill, and then we have essentially a mass or a gravity type retaining wall. So here's an exploded isometric view of the components that make up bin wall. So just in generally speaking, it's fairly simple components. So we have our horizontal stringers shown here with 2 bolts per connection to the vertical T. So this T is essentially what separates each adjoining bin. We then have the transverse spacers, which we vary in length essentially to increase or decrease the depth of the bins as we increase the height. And then we have the grade plate and top stiffeners at the top and the bottom of the walls. So, lightweight, nestable components very easily shipped to remote sites, which is kind of where we see bin wall primarily used. Doesn't really require any form of specialized labor or specialized equipment to install. So just to give you an idea of the geometric configuration, so typically we can increase the wall height in 16-inch segments for 406 millimeters. Usually the maximum height for bin wall was around 8.5 meters, again, depending on the batter, the live loads, et cetera, that we're designing for. We do have 6 standard bin depths as well, A through F. The maximum depth of the F bin is 5 meters. So typically with deeper bins, we're reducing the toe pressures, and as we get up to 8 meters high, usually it's the toe pressures and the geotechnical considerations that are the limiting factors within the design of bin wall systems. So here's a photo showing bin wall as an entry to some bridge plate low profile arches. So this was a project over in St. John, New Brunswick at the Canafort LNG facility. So a full steel solution, which is what we love to see on all of our projects, of course. So we had the bridge plate structures, the bridge plate backing head walls, and then bin wall used for wing walls. So again, another photo of bin wall in the wing wall application for a bridge plate culvert. So often this is used in conjunction with either a cast in place head wall or an anchored steel head wall, as I showed before. So often cast in place is going to be a good solution if you're expecting high debris flows through the culvert. Can really be the best method of protecting the bridge plate structure. Bin wall in general is a fairly robust retaining wall system capable of handling fairly high settlements, high loading conditions, and fairly harsh stream conditions as well. It can be installed in submerged conditions. The one thing to note there is that it's important to ensure that the backfill that's used won't actually be washed out of the bin. So typically in submerged conditions, we'll make sure that we're specifying material that's larger than 3 to 5 millimeters or so. If that's difficult to source, we can also line the interior of the bins with a non-woven geo just to prevent migration of the fines. So one last thing we've also done with bin wall is essentially remove the back components and actually just designed it as a steel-faced MSE wall. So this can definitely be a cost-effective option if you need a robust facing material on a remote site, and also when there are challenging or narrow footprint constraints. So essentially in this case, we designed a dowel type connection between the steel facing and the geogrid, and the geogrid obviously was designed to provide the lateral support for the wall. All right, so that provides a fairly nice segue into MSE walls. So these have quickly become a very common, popular type of end treatment for structural plate bridges and culverts. So just a quick introduction to MSE walls. There are essentially just three components that make up any MSE type system. So number one, we have the backfill material, which is typically a well-graded granular backfill compacted to 95 or 98% standard Proctor density. Secondly, we have the soil reinforcement, which could be either an extensible or inextensible reinforcement. So extensible just refers to any plastic geogrids like polyester that we use manufactured by Tenkata. We also have inextensible reinforcement, which would refer to any steel mesh or steel strips, usually required for fairly high walls, typically above and beyond around 9 meters. So the last component is the facing unit. It could be a wire mesh form as shown here. I've also seen concrete panel systems, GEOCELLs, gabions, or just woven geotextiles. There are certainly a lot of different types of options, some of which I'll talk about in the next few slides. So what I would say is probably the most common basic type of MSE system is the wire mesh form wall. So a few primary components. Of course, we have the wire mesh form itself as the facing material. We have the primary geogrid, which is the actual soil reinforcement. So the Armtec system just has a wrapped face, so typically we specify around 1 meter return on the top side of the layer. We then have a non-woven geotextile separator, just standard Armtec 200 material, and that's basically to prevent a migration of the engineered backfill into the cobble and rock facing material. So the cobble and rock facing is really a protective measure for the wall. So it's a fairly simple system, has a lot of advantages, particularly as an end treatment to structural plate. It's certainly economical, both in terms of installation, upfront material costs, and shipping costs. We can fit a lot of end treatment on the back of a truck. These are nestable components and just rolls of geo, essentially. So freight is typically a minimal consideration. It also has a very complementarian installation method with structural plate products. So, both require engineered, well-graded backfill. Both require compaction of that material to, 95% standard Proctor density and roughly 8-inch lifts. So, when it comes to construction costs, it's typically not a huge cost adder when we're talking about these type of MSE walls used in conjunction with a bridge plate arch, for example, as shown here. So if you've been to Whistler, you might have actually skied through this structure. It's a bridge plate ellipse supplied for the 2010 Winter Olympics, I believe the women's downhill. So just again to highlight a few of the applications of wire mesh form walls. One of the last things I'll mention is that they're fairly robust systems, really ideal for compressible foundation soils. They can handle a fair amount of settlement fairly well. We can also do vegetated slopes. These are ideal if we have an environmentally sensitive site or if we need a green wall. So in these cases, we just supply mirror mesh or an erosion control blanket, potentially in lieu of the non-woven geosynthetic and the cobble facing material. And of course, we need a plantable backfill as well. So the particular wall shown here was installed for a project in Oakville, Ontario. GEOCELL is another facing material that can be used in an MSE configuration. Works very well as an end treatment with structural plate products. In essence, GEOCELL is a cellular confinement system, typically used in conjunction with weaker soils. So we use it to create what we would call an engineered grade composite. So by backfilling and compacting the individual cells, as you can see here, we have the mats, cellular confinement. So we compact the weaker soils in there, and they can essentially just emulate the characteristics of the stronger granular soils. So these are usually beneficial if we have a fairly high amount of cover over a buried structure, and of course a requirement for end walls. But by using the GEOCELL, usually we can reduce the amount of potentially more costly granular fill that needs to be brought to site. So here's just a photo of the GEOCELL used in conjunction with a bridge plate single radius arch. All right, so lastly, in terms of end treatment, one of the most cost-effective options is certainly just a beveled end. So if you have the room or capability of doing this on site with just your sloped embankments, it can really be by far the most cost-effective and simplest option. One important thing to note with beveled ends, whenever a structure is cut, you need to remember we're talking about flexible systems. They rely on the soil support around the structure. So we do require concrete collar reinforcing because we're interrupting that ring compression. So usually when a structure like this is cut, the plate strength in the cut areas is just limited to the bending strength of the corrugation. All right, so at this point, I'll go through a few quick project case studies and just general applications for structural plates. So by far the most common application we see for multi-plate, even bridge plate, would be culverts and stream crossings. Just on this slide, really wanted to highlight the various profiles that we're able to achieve, and again, the variety in end treatment options that are available. So didn't really talk about gabions, but that's another option that's available. Just woven geosynthetics or GRS walls as well, something we've gotten into, and then beveled end treatments just with a cast in place collar reinforcement at the end of the structure is very common as well. Here again is an example of a bridge plate box culvert, again with a cast in place head wall and wing walls. So typically a fairly costly option, but can definitely be a great way to protect the structure from high debris and harsher conditions. Here's an example of a low-profile bridge plate arch or 2-radius arch, so just under 9 meters in span, 3.3 meter rise. Just to again highlight the lightweight nature of these systems, so we have 5 plates that are used to make up this the periphery of this structure, and so the rings were just assembled in a staging area beside the site and then lifted into place. So typically with a structure of this size, we have cast in place footings. We can supply precast footings as well for smaller structures. So Armtec would supply an unbalanced channel here, which provides a bolted connection for the footing plates of the arch. So the structure was actually supplied for the Ministry of Highways, Highway 905 in Saskatchewan, and then we also supplied the wire mesh form MSE head walls as well. So this is a project in Calgary at the Western Headworks Canal. Again, just to highlight the variety of shapes that are possible with bridge plates. So this is a bridge plate and stream crossing application, and then an underpass application as well. We've also seen things with end treatments with architectural panels and things like that. So we're always willing to look at other considerations when it comes to head walls. And then bridge structures is definitely a growing market for structural plate. As we've increased the depth of the corrugation in the past couple decades, this is an area where we're now able to achieve spans in excess of about 20 meters. So we can fairly easily span a 2-lane road or highway. So the structure here, there are a couple pairs of these along Highway 1 outside of Banff here in BC and Alberta. This is, again, the ski hill ellipse that I mentioned before. And then just in terms of end treatment, beveled ends are fairly common. And then again, cast in place head walls, again, a common option. We've also supplied bridge plate for railway overpasses. So this is a project that we did in the United Kingdom. A bit of a unique application where it had to be installed over live railway lines. So what they actually did was assemble the bridge plate in a staging area next to the site and then just drop the full assembled structure, I believe in two halves into the footings. So in the mining sector, we see bridge plate used fairly often for overpass systems. So usually these are remote sites that we're talking about where it would be difficult to get, say, a precast girder segment or something like that. So really here, just to highlight the structural efficiency of these designs, this was a project we did at the Highland Valley Copper Mine. We had a sloped installation, 3 meters of cover at the front end of the structure and then 9 meters at the back end. And then we were designing for a 1.4 million pound loaded Cat 797. So very high live loads that we're talking about. You can see in the crown of the structure, obviously we're experiencing fairly high bending moments in terms of design. So sometimes in those cases we'll have some sort of reinforcement, typically just some additional bridge plate ribbing to add a bit of stiffness to the crown of the structure. So here's a photo of the completed and backfilled system. So ultimately it was 8 millimeter thick bridge plate, which is the thickest plate that we're able to supply. It was about a 16 meter span, I believe, a single radius arch, and we also supplied it with precast GRS head walls. Again, in the mining sector, fairly common application for multi-plate and bridge plate are reclaim and escape tunnels. So the two photos on the left there, both before and after shots of a reclaim tunnel at Copper Mountain Mine. So this was the 6 meter diameter reclaim tunnel supplied there. A couple interesting things about this project: we actually supplied it with a bend, which you might be able to see there slightly in the top photo. So we can do all sorts of custom fabrication with these systems. One thing to note in terms of stockpiles or reclaim tunnels, usually for these applications we're cutting hopper openings into the crown of the plate. So again, we're interrupting the ring compression, which is why we have these rolled I-beams acting as reinforcement to help induce ring compression in the structure. Then escape tunnels. This was an escape tunnel supplied at the Endako mine. So again, just to highlight, we can do all sorts of custom fabrication. We can manufacture bends and elbows and all those sort of things. So this is another multi-plate reclaim tunnel locally here in BC in Port McNeill. So this was supplied to the Orca Sand and Gravel quarry, so the largest sand and gravel quarry in North America, or I believe in the Northern Hemisphere. So this was a 3.6 meter diameter tunnel, 7 millimeter thick plate designed for a 31 meter high stockpile. So very high dead load designed for in this case. Ventilation shafts is another area we've seen multi-plate used. This was a bit of a unique project for the Mosaic Potash Mine near Esterhazy. I believe I'm pronouncing that right, in Saskatchewan. It was a 4.5 meter diameter multi-plate. We supplied it with the STRATA-CAT polymer coating because there were fairly corrosive atmospheric conditions. And then we also supplied it with a waterproof seam sealant, which is another possibility if you need to mitigate the water that might be going through the structure at the bolted connections. And then we also had custom fabricated elbows that we manufactured as well. Vertical shafts is another fairly neat application for structural plate products. These are actually both applications of our tunnel liner plates, so the two-flanged liner system. Both black steel, so fairly common, and then we see the tunnel liner plate being used here in conjunction with ground freezing. All right, lastly, culvert and bridge rehabilitation is another application of structural plate. So I'll just use this slide to give a bit of a plug for an upcoming webinar we have, will be coming early next year. I don't believe we have a date set yet, but keep your eyes peeled for that if this is something that's of interest to you. So definitely a growing market for structural plate products. We can easily match the profile of an existing structure, whether it's corrugated steel or a concrete system. So we can match the structure, size it down slightly, so we can either slip line that structure, or we can assemble with our tunnel liner plate the structure inside of the existing one. So like I said, keep your eyes peeled if this is something that's of interest to you. Just a quick case study. This was a project that we did for the MTQ bridge rehabilitation in Monk, Quebec City. So essentially we had a deteriorating concrete archway that needed rehabilitation fairly badly. Fairly sensitive transportation system here where we couldn't interrupt the traffic flow. So relining was the best option. So we matched the profile of the archway with our bridge plate. We had a single radius arch. It was assembled outside of the structure, slip lined in, and then grouted in place. So we can do these sort of relines with any structural plate product, tunnel liner plate, multi-plate, or bridge plate. All right, so that concludes my portion of the presentation. Thank you all very much for joining us. And with that, I will hand it over to Janine to wrap things up.
Thank you, Heba, and thank you, Drew, for your presentations today. And thank you, everybody, for joining today's webinar. We hope you enjoyed the presentation and found that the information is valuable. Our question and answer period is coming. We will probably go 5 minutes after, so feel free to submit your questions. If we don't get to them, we will submit or respond to you by email. I will be going over a couple of housekeeping items, but stay tuned for our Q&A session. We'll just start in a minute. As you saw in the presentation, there are numerous technical considerations involved in the design of buried bridge structures. When the need arises, Armtec can certainly help you and support you through the selection and design process. Feel free to contact us at any time. The presenter's contact information is shown on the screen. They can certainly help answer your questions or connect you with a local representative near your project location. We hope you enjoyed today's presentation, and we look forward to you joining us for our next webinar on December 16th, titled Armtec Engineering's Top Picks, Case Studies and Design Review, where some of our top professional engineers will review their favorite projects and design challenges from recent projects. It will be our final webinar of the year and a chance to get caught up on your CPD credits, so we look forward to seeing you there. Please remember, if you would like to view any of our prior webinars, you can look them up on YouTube by searching for Armtec. We are in the process of finalizing our exciting 2017 webinar lineup, so to stay informed, please stay connected with us. You can follow us on social media through Facebook, LinkedIn, and if you know someone who was unable to make it today, they can view our webinars on YouTube. You can also get all the latest on Armtec by following us on our website, armtec.com. We do value your feedback, and at the end of the webinar, there will be a quick exit survey. We would like to know what you think of the event. Question 6 will ask if you're interested in receiving more invitations for Armtec webinar events. Please, please choose yes. Due to strict Canadian anti-spam legislation, we are required to have your consent to receive future invitations for webinar events. So if you want to ensure that you're on our invitation list, please choose yes. If you choose no, you will be permanently removed from all emails. We don't want that to happen. So thank you for joining again. And right now, we'll move into questions and answers, which will be moderated by James.
Thanks, Janine. So there's some great questions here. Please keep adding them if you're in a boardroom today. Maybe designate someone. If we don't get to them all, we'll definitely make sure we get to them via email. So to start, to what extent does Armtec assist with project engineering and construction services?
Okay, I'll answer that one. We get involved quite heavily with assisting at the front end, working very closely with consulting engineers to assist them with budget designs, with alignments, with profiles, choosing the right shape, all the way up to site services as well. So, you know, beyond doing the budget or initial engineering with consultants, then we take over on structural design, as we do that all in-house here with our engineering department for all of our bridge plate, multi-plate structures we presented here today, as well as our end treatments. And then once the product is shipped to site, we also have our local representation there on site with you, with the project managers, to assist in any way we can during assembly as well as backfill.
That's great. Thanks, Eva. There's a question about live loads. It actually came in prior to you showing that mine truck. That was, I guess, a 1.4 million pound mine truck. But we'll ask it anyway. What is the largest live load that can be accommodated by these structures?
Yeah, sure. So I'll tackle that one. I mean, yeah, we can handle fairly high live loads. Again, it's kind of a function of the actual span of the structure, as well as the depth of cover. So we can handle the fairly heavy mine haul trucks. You know, if we're talking about a single radius arch, obviously that's going to be able to handle those, you know, heavy live loads better than a box culvert or something like that. So yeah, it's kind of a case-by-case basis. Typically, we can increase the depth of cover to help distribute those live loads. But yeah, it's, you know, kind of project-specific applications. So if they're very heavy live loads, railway loading or something like that, it's definitely something we can look at and potentially address.
Excellent. And this one did come in before the session, and you did spend quite a bit of time comparing them, but we might as well just do a quick summary. Can you compare steel to concrete and treatment options and the factors for those considerations?
Yeah, for sure. So those are considerations that are addressed in the AASHTO standards. So they're usually corrosion criteria for you know, any steel facing systems. So those are typically the design considerations. Obviously, when we're talking about roadway applications or highways, there are always, salting considerations and potentially corrosive conditions for a steel system. So in those cases, concrete can definitely be an option that will provide a longer service life than potentially a steel-faced retaining wall.
Excellent. And Heba, this might be a good one for you. I have a project with pipe arch culverts for installation where native soil is soft and settlement prone, so that the structure will be on piles, especially the wing walls, which will experience overturning soil pressure. I don't know if you want to respond to that, or.
Yeah, so if I understand the question correctly, that person's asking whether the design would have special considerations with being on soft ground. Typically, or generally speaking, full periphery structures are better suited for applications with lower than normal foundation bearing capacities in general. But to a point, at the end of the day, these structures are going to be buried, and the foundations will have to support the weight of the structure as well as the soil column above it. So the foundation capacities will have to have sufficient strength to support that. That is usually best designed by a geotechnical or foundation engineer that will be able to address that. However, again, generally speaking, if the foundation soils are soft or mucky, the best thing to do is to excavate below the grade line and backfill to grade with suitable material that will adequately support the weight of the pipe and the backfill. If that's not prohibitive, again, if that's prohibitive, there are other ways to tackle that by reinforcing perhaps the foundation soils, but again, that's usually done by a more geotechnical specialized consultant. As far as the retaining wall question or part of the question, that's usually a separate design element, and most wall designers will supply a maximum anticipated bearing pressure that the foundation has to support. So again, it depends also on the type of wall that's being designed, whether it's cantilever or sheet piling. So it's a very general question in that aspect, but we can certainly assist if there's a specific project with more detail. We can certainly assist with that.
Excellent. To our audience, I know we're running up time here. We're 10:05, so I'm going to take one more. There were several technical questions that came in, and please, if you want to get them in there, feel free to. You'll also be able to get them in on your exit survey. And I think what we may do in this case is we'll have a look at the questions. If they're kind of universally applicable, we may include them in an update on our blog or on our website for everyone to see kind of what the responses are here. There's some great questions came from the north. So how can frozen conditions affect soil structure interaction and design criteria? And I'm going to tack on the next one because it's kind of specifically related to the same question. What additional control or loading do you suggest for thermal expansion and contraction of corrugated steel pipes used in long span culverts? So this is all the same question coming from the north here.
Yeah, so in terms of thermal expansion and contraction, soil steel structures are, very well suited for minor settlement. They are flexible structures, so they are meant to move a little bit. So those types of forces are normally not a concern, depending on the severity of that. But generally speaking, that's not something we worry about. And sorry, James, can you reiterate the first half of that question?
Well, there was just a general question about frozen conditions, and it is coming from the far north. So, for example, right, we're dealing with issues like frost heave, and there was a concern about cracking, or if there's any kind of specific considerations in the far north that might need to be considered.
Right, so generally we have very stringent requirements for backfilling, especially in winter conditions. The soil has to have certain properties. They have to be well-graded, free-draining material that can be compacted to at least 95% standard Proctor density. So the soil has to adhere to these sort of specifications that we detail on our drawings, and as such, winter construction can be tricky, but there are ways to ensure that there are no frozen materials anywhere in the backfill material. So that all has to be removed prior to backfilling, as well as techniques to heat and torp the backfill to make sure that none of the issues arise with frozen material.
Mm-hmm. And I think you've kind of answered the next one related to the far north, which is what considerations are used for embankment fill experiencing a lot of freeze-thaw cycles, which I guess you said need to be free draining is the biggest consideration. Is that correct?
Yeah, correct. As well as the movement in the steel portion itself is not a large worry for us because they are meant to move and flex.
Mm-hmm. Excellent. There are a lot more great questions that came in, so everyone, we will respond to those directly. We have your email address kind of associated with each question that came in, so you'll receive a response from Heba and Drew on that, and then we'll maybe have a look at sharing them as well. With that, many thanks to our audience for your time today. Many thanks to Heba and Drew for their time. Please remember to join us again on December 16th and keep an eye out at armtec.com. The homepage always features the next upcoming webinar. You can provide feedback in the exit survey. Please, as Janine mentioned, number 6, if you ever want to hear from us again, please choose yes to that question. And also number 4, you can indicate whether you have a project that you'd like us to get in touch with you about. So without further ado, enjoy your day and have a wonderful weekend. Thanks, everyone.
Thank you, everybody. Goodbye.